Okay, now the recording has agreed to start. I'll just need some confirmation again that you can see my screen. Good.
Yes.
So we'll start on a new topic today. It's actually rings and fields, but we'll start with rings. So it's just an extension of what we've been doing in groups, but adding some more structure, algebraic structure, operations, more than one operation onto a given set. So here we go. We'll say let R be an empty set with two binary operations. The first one will denote it by this symbol plus, and the other one is this dot that represents multiplication. So these two operations will be addition and multiplication. That's what they'll be called, respectively. So we say that R will be a ring. If we consider this set R under addition, we have an Abelian group, additive, written additively. And then if you consider the same set R under this operation, this dot, we will get a semigroup. Now, I'm assuming you learned about semigroups in SMA303. You recall what a semigroup is? Can someone tell us what a semigroup is? So a semigroup basically is required to satisfy only the first two properties of a group, the closure and associativity. If it's closed and associative, that's enough. That makes it a semigroup. Then we have two more properties here. When you are learning about binary operations, you must have learned about this distributive property, right? Wakanene?
Yes, sir.
So idea hapo bwana, no one is answering. Did you learn about the distributive property?
Yes.
Of binary operations over others. So this third property says that the multiplication must be distributive over addition. So any three elements you pick from the set R, this multiplication will be distributive over addition on both the right and the left. So these properties, if they're all satisfied, then we say R is a ring, and we denote a ring in this fashion, this last this angle brackets, the set itself, and the two binary operations in that order, addition followed by the multiplication. Now, there's no reason why you must use R. I just happen to use R, but you can use any letter. It's just an empty set. Whichever letter you choose to represent it by does not matter. You just need to know it's an empty set. And we have two binary operations defined on it, which satisfy these properties. Now, the important thing is to get the difference between a ring and a group. A group has only one binary operation defined on it, but for a ring, we need two binary operations. So anytime you're talking about a ring, you need two binary operations. One of them will be called multiplication, which is this dot for us, and the other one will be called addition, which is this plus sign. So that's it. So we can look at some simple examples of rings. The other thing is you can break these properties down further. For an additive Abelian group simply means you are looking at 5 properties. The 4 properties that make it a group plus the Abelian property, that's 5 properties if you are to list them out. So if you want to check if a set is a ring under some operations, you need to check those 5 properties under addition. A multiplicative semigroup gives you 2 more properties. That is the closure under multiplication. And although when you talk of a binary operation, closure is implied, so it's a bit redundant what I'm saying. But I think it just emphasizes the point. So closure and associativity, that's the only two properties that are required. You can have more properties, but we don't care for this. The only properties required for under this to be a semi-group is closure and associativity of the binary operation. And then once you have those two, we have 5 properties here. We have 2 more, that makes it 7, plus these 2, that makes it 9. So you need a total of 9 properties to check. If you want to check that a set is a ring under any 2 binary operations given. Also, we don't always have to use these symbols to denote addition and multiplication, but this is convenient for us. This plus will always denote addition. This will always denote the multiplication operation. But that's not a must. You can always use, it's possible to find other books using different symbols for those operations. So the identity of the abelian group is normally called the zero of the ring, and we denote the additive inverse of any element in the ring as negative a. Okay, that is important. So when we add an element a to the additive inverse of b, we shall, instead of writing it as a plus negative b, we shall just write it as a minus b. So we define subtraction as this, where you add the additive inverse of some element to another element in the group. And then for simplicity, we shall not, we shall leave out this multiplication as a binary operation, the dot. Instead of having a dot b, we'll just have ab to mean multiplication. The binary operation of multiplication will now be simplified just like that. We put a next to b, and that would mean ab. Are there any questions on this? Can you hear me?
Yes.
Hamuna swali? So we move on to the next part. Yeah, we have some examples of rings. So if you consider the integers, I think you're familiar with all these symbols, what they represent. This is a set of integers, and you can consider it under the usual addition of integers and the usual multiplication. That will be a ring. The same is true for the rationals, the real numbers, and the complex numbers. These are all examples of rings. The ring of integers here, modulo n. If you consider Zn, integers modulo n, they will form addition. This is under the addition modulo n and also multiplication modulo n. We have seen how this works before. So those two operations will turn this set Zn into a ring. The other examples of rings as well, I think I've repeated this. This is the same as number 2 and 5 are the same. Also, if you consider a set of all n by n real matrices, real means the entries are real numbers. This will also form a ring under the usual addition and multiplication of matrices. So they have to be square matrices. You want them to be a ring because you need to be able to multiply them. If they are not square, you might not be able to multiply the matrices. So if you consider all the set of all n by n matrices, that will be a ring under the usual addition and multiplication of matrices. So as usual, anytime you are talking of a ring, it has to be very clear in your mind what the set is and what addition and multiplication are, how they are defined. That has to be very clear anytime you're working with a ring. So we have given simple examples. I will not dwell too much on the examples, but this shows you that they actually exist. We have some infinite rings. We also have some finite rings. Infinite means they have an infinite number of elements, and finite is just they have a finite number of elements. So there's a special ring which we call the commutative ring. So we'll define it. So a ring R is said to be commutative if for any two elements A and B in the ring, the multiplication is commutative. Remember, under multiplication, a ring is only required to satisfy two properties. So if in addition to those two properties, that is closure and associativity, if in addition to that, it happens that it is also, the multiplication is also commutative for all elements in R, then we say the ring is a commutative ring. And the opposite is that of that is non-commutative. So we have commutative rings, and we also have some non-commutative rings. Maybe I should go back here to look at some examples. So these first two cases are examples of commutative rings, because multiplication in all these cases will be commutative. This number 4 is an example of a non-commutative ring, because multiplication for matrices is not commutative. So we have at least an example from each group. We have the commutative ones, the first two, and even the third one is a commutative ring, because when you're adding this function, multiplying this, you can switch it. You can switch order and still get the same answer. So maybe this number 3, you need to, this multiplication is not composition of functions. It's actually multiplying the functions. So for instance, if one function is x squared and the other one is x cubed, if you multiply them, you get x raised to 5. So this is actually multiplying the functions. And at the top here is adding the functions. That's the addition. So this is also a commutative ring. But this number 4, this example labeled number 4 is a non-commutative ring. So that defines a commutative ring. And remember that a ring is not required to be commutative, but some rings may be commutative. And when they are, we will call them commutative rings. And secondly, that the commutativity is only with respect to multiplication. Under addition, we've already said that R will be an abelian group, so it's already commutative under addition. We do not add any value to talk of commutativity under addition, because it's guaranteed for any ring. It's only under multiplication that it is not guaranteed. And therefore, when it happens, we classify the ring as a commutative ring. Any questions? So here are some properties of rings. Did we finish this? There's some things I left out. Maybe they come later. So if you multiply any element in the ring by 0, 0 is the additive identity. We agreed that one is called 0. We shall always represent it with this symbol 0. 0 is the additive identity of the ring. So under addition, 0 is the identity. Whatever it is, whether it's a matrices, we shall always call it the 0 of the ring. So if you multiply A by the 0 of the ring, any element by the 0 of the ring, you will always get 0. And if you multiply A by the additive inverse of B, you simply get the additive inverse of AB, which is also the same as multiply the additive inverse of A by B. So we will not prove this, but there's some notes I gave out where you can find the proof for this. The handwritten notes, the ones from last year, the proof for this is there. So the other definition, it's just notation. When we have A multiplied by itself m times, we shall just denote that by a raised to m. And if you add a to itself m times, we shall write that as a multiple of a. So ma simply means a added to itself m times. Just give me a minute. I need to. We have some noise from. So we can continue. I think this. So here is another property some rings may have. Not all of them will have it. So a ring with unity is a ring in which the multiplicative semigroup has an identity element. So again, remember under multiplication, the ring is only required to satisfy two properties, but it may have extra properties. You have seen one extra property that it may have, may or may not have rather. And that was the commutative property under multiplication. So there's one more property here we are considering again. That is a unity or the identity, multiplicative identity. So if there's an identity under multiplication, we say that it's a ring with unity. So the identity is simply an element that behaves like this. AE is equal to EA is equal to A. So usually we denote the identity element of a ring by 1. 1 now, when we write 1, we will mean the identity element of the ring, regardless of what the ring is. 1 here will no longer act as a number, but it will act as a symbol to represent the identity element in the ring. So going forward, we shall denote the identity element of the ring by this symbol, 1. So if it happens that the ring has an identity element, multiplicative, then it's also possible for some of the elements to have a multiplicative inverses. And that is A inverse. We denote that by A raised to negative 1. So some elements may have inverses and others may not. And those that have the inverses, we shall denote their inverses using this notation. So the inverse of A will be A inverse. And they also have a special name. Any element that is invertible will be called a unit. And A raised to 0 will be defined as equal to 1, where 1 represents the identity, the multiplicative identity in the ring. You can hear me?
Yes.
Yes.
Good. So again, maybe we can just to illustrate that using our examples. So in all these examples up here, the multiplicative identity is just the usual number 1 itself. So these are all rings with identity. The same is true for Zn. Zn is also a ring with identity. Even number 4, the set of n by n matrices is a ring with identity because the identity element here will be the identity matrix. So these are all examples of rings with identity. Later on, there are some rings that don't have identity. I have not put any examples here, but I can explain that later. So let's look at another special type of ring. So now, if it happens that all the non-zero elements in a ring form a group under multiplication, then the ring will be called a division ring. So if it happens to be a division ring and it's commutative as well, then it will be called a field. Again, we can go back to our examples, see which ones are division rings and which ones are not. So if you look at the integers will not be a division ring. Why? Why? Maybe it's important to first read the definition before we go back. Just look at the definition first of a division ring. So it means if you take all the non-zero elements and consider them under multiplication, they will form a group for a division ring, that is. So that's the only consideration we need to take into account when doing this classification. And if it happens that the ring is also commutative and it's a division ring, then we call it a field. So let's go back again here. So the ring of integers is not a division ring because some elements, the non-zero integers don't form a group under multiplication. So this is not a division ring. These rationals, if you consider the non-zero rational numbers under multiplication, they will form a group. So this happens to be a division ring. Now it also happens to be a field because it is commutative. It's a commutative division ring. The same is true for the real numbers and the complex numbers. So these last three are all division rings. Now Zn will only be a division ring if n is a prime number. If n is not prime, then it will not be a division ring. The set of n by n real matrices, if you consider all of them without any discrimination, they will not form a group under multiplication of matrices. The only way they will form a group is if you consider only the invertible ones. That is a general linear group. But if you are thinking about all the matrices, they will not form a group under multiplication because some matrices will not be invertible. So this number 4 here is an example of a ring that is not a division ring. This ring of matrices is not a division ring. So Zn we see depends. It will be a division ring depending on the value of n. If n is a prime, it will be a division ring. If n is not a prime, it will not be a division ring because some elements will not have inverses under multiplication if n is not prime. So our commutative, I think we have gone through this, so we can move on to the next. I think this gives the same examples that we looked at earlier, but it adds one more example. If you consider this set of 2 by 2 matrices over the complex numbers. So for this set, we consider matrices whose entries are complex numbers. So matrix is structured as follows. The first row will just have A and B. And then the second row will have the negative of a complex conjugate of B as the first entry. And the second entry is a complex conjugate of A. You learned about the complex conjugates. Isaac, you have to save me here again. Did you learn about, you know what conjugate is?
Yeah, we learn about them.
Okay, so this is actually, you can check that this is a ring under the usual addition and multiplication of matrices. So this, any pair of matrices you pick in here, if you add them, you'll get another matrix that is in the same set H, and so on. You can check check that this is an abelian group under matrix addition, and check that it's closed under matrix multiplication. And we know that matrix multiplication is associative. So, and also we know that matrix multiplication is distributive over matrix addition. So this will form a ring. Now, under multiplication, we can check that all the elements will be invertible by looking at the determinants. The determinant is simply computed as this. Determinant, you multiply A by the complex conjugate of A, then you subtract B multiplied by the negative complex conjugate of B. So because of these two negatives, you will end up with a plus. Minus minus will give you a plus. But we just know that if you multiply any complex number by its conjugate, it's the same as the magnitude squared of the complex number. So this is the magnitude squared of A, that's the magnitude squared of B. And that cannot be equal to 0. I think maybe I left out a condition here. Okay, yeah, it's fine. I didn't leave out any condition. If it's a non-zero matrix, then this quantity will never be 0. So any non-zero matrix will have this property. The determinant will not be 0. So it means any non-zero matrix will be invertible. We know that the identity matrix is also in here, belongs to this set. So what is left? So it means that under multiplication, this set H will also be a group. This is something you can check. Under multiplication of matrices, this set H will be a group, and they have not really the whole set, but the non-zero matrices in the set H will form a group, because they will all be invertible. And because of that, this is a division ring. And it's an example of a non-commutative division ring. So here is another definition. We define an integral domain. So a commutative ring with unity is an integral domain if x multiplied by y equals to 0, implies that x or y must be 0. One of them must be 0. So it says if you pick any two non-zero numbers or any two numbers and multiply them to get 0, the only way that can happen is if one of them is 0 or both. But at least one of them should be 0. So such a ring is an integral domain. This is true in the ring of integers. The real numbers also will be an example. Now, Zn may or may not be an integral domain, because that only happens if n is prime. So that fixes the definition of integral domain. So basically, it simply means if you multiply any two numbers and two elements of the ring to get 0, one of them must be 0 if it's an integral domain. So Zn is an example. If for instance, if you pick Z4, for instance, it's possible to multiply 2 times 2 in Z4 is equal to 0, yet 2 itself is not 0. So Z4 is not an integral domain. But if you have something like Z5, Z5 will be an integral domain, because any non-zero numbers in Z5, if you multiply them, you will not get 0. So as long as n is a prime number, Zn will be an integral domain. It's actually a field, but here we are interested in the integral domain property. So theorem here. I think I left out something. It's supposed to be every division ring is an integral domain. The theorem says if any division ring will be an integral domain. So remember, we say that in a division ring, all the non-zero elements form a group under multiplication. And that means all the non-zero elements are invertible. So that's the property we're going to use, that any non-zero element in a division ring must have an inverse. It must be invertible. So let an inverse under multiplication. Remember, I told you when you think about addition in a ring, every element has an additive inverse. Every element has the additive identity exists also in the ring. The only thing that may or may not be there is the multiplicative identity. But if it is there, then you call it a ring with unity. So this is important in this definition. The commutative ring with unity is an integral domain. Commutative, let me not go into the details of this. There's a reason why you need commutative there. So if xy is equal to 0, let R be a division ring. We are proving this theorem that every division ring is an integral domain. So what we need to prove is that if you multiply any two elements in a division ring and get 0, one of them at least must be 0. So let's assume that is the case. We have multiplied two elements and we get 0. So suppose one of them, say x, is not 0, then it means it's invertible. And therefore we can multiply both sides of this equation by x inverse. And when you multiply x inverse by xy, x inverse and x will give us 1, and then 1y will give us y. But all that, if you multiply this right side by x inverse, you still get 0, because we saw earlier that if you multiply any element in a ring by 0, you will get 0. So if x is not 0, it turns out that y will not be equal to 0. So at least y will be equal to 0, sorry. So if one of them is not 0, the other one must be 0. You can mirror the same argument for y. If it's y that is not 0, then x, so you can always multiply by y inverse on the left, and you are left with only x and 0 on the right hand side. So the same argument can be mirrored for y if y is not 0. So basically you have proved that if you multiply any two elements and to get 0, one of those must be 0. So every division ring must be an integral domain, but the converse is not necessarily true. An integral domain does not have to be a division ring. So for instance, the ring of integers is an integral domain, because if you multiply any two integers to get 0, one of them must be 0. But it's not a division ring, because the non-zero integers do not form a group under multiplication. So here is another definition, the zero divisors. So if you have a non-zero element in a ring, it will be called a right zero divisor if we can find another element y in R such that if you multiply x on the right of y, you get 0. So that's what makes it a right zero divisor. So left zero divisor is simply if you multiply x on the left of y, if you can find some element y such that x multiplied on the left of y will give us 0, then we call x a left zero divisor. If it works on both sides, then we call it a zero, simply call it a zero divisor. Let's see if we can illustrate this. Let's consider the ring Z6. If you multiply 2 by 3, you will get 0. So 2 and 3 are examples of zero divisors. Same with 4 and 3. 4 is also a zero divisor because you can find 3. If you multiply 4 by 3, you will, and this can work on both the left and the right. That's why we are not saying left or right. They're just purely zero divisors. So here is a there's a typo here. I think. No, I think it's fine. If you multiply these two matrices, you will get the zero matrix, right? There. Yeah, it's true. So you have two non-zero matrices which are multiplied and we obtain the zero matrix. So this one will behave like a left zero divisor. This one is a right zero divisor. So I have not checked if it can work, they can work on both the left and the right. You can check that yourself. But now here, the important thing is that we found two non-zero matrices, which when multiplied will give us the zero matrices. So we found some zero left and right zero divisors in the ring of 2 by 2 real matrices, right? So in the ring of integers, the only zero divisor is 0. And this is true for any integral domain. You have an integral domain, the only zero divisor will always be 0. The same is true in Z5. Z5, the only zero divisor is 0. How you check is the same thing I've done for Z6. You try to find if you can get any two numbers which are not both 0. If multiplied, if you can find such two numbers whose product is 0, then you have some zero divisors. So in Z5, you can check that all the non-zero numbers, if multiplied, will never give you 0. The only way you can get 0 is you multiply some number by 0 itself, modulo 5. The same is true in the ring of integers. The only way you can get 0 is by multiplying two numbers where at least one of them is 0. So the only zero divisor is 0 in Z, and in same and Zn, as long as n is a prime number, then Zn will be an integral domain, and therefore the only zero divisor it will have is 0. So definition here, we define a subring. Yes.
You can go to the previous slide.
This page?
The other one.
Yeah.
Yes. Thank you.
What do you want with the page? You have a question?
I want to take a screenshot.
I have shared the slides.
Oh, okay.
I don't know if Eugene is around. Maybe Eugene is relaxing at home. Is Eugene around?
Yes, we have received the notes.
Ah, okay. I just sent them this morning, so maybe some
Yes,
of
we
you,
have.
maybe some have not downloaded it yet. But you already have them, so that's fine. So here is another subtopic we need to cover. So we talk about subrings. The same thing we did with groups. We talked about subgroups. If you have a ring R and S is a subset of R, then S will be a ring if S itself is a ring. I mean, S will be called a subring if S itself is a ring. So a subring is just a smaller ring sitting inside another big ring, using the same binary operations in the bigger ring. So the simplest cases of subrings would be the set containing only the zero element and the set containing R. I mean the whole ring R. These are the simplest examples of subring you can think of. We saw earlier that the integers and the rationals are all rings, but they are also subsets of a bigger ring, the real numbers. So they become subrings of the ring of real numbers under the usual addition and multiplication. So we make some remarks here. If you, in a ring with unity, a subring may have a different unity from that of R, or it can also fail to have unity. So for example, the subset, if you consider Z10 and you pick this set consisting of just the even numbers, 0, 2, 4, 6, 8 in Z10, then this will also be a ring because this set will form an additive Abelian group under addition modulo 10. And also under multiplication modulo 10, it will be closed and associative. And we know very well that addition is distributive, rather multiplication is distributive over addition modulo 10. So this will form a ring and therefore will be a subring. But now we notice the following. Z10 has the identity element is 1. But here the identity element is 6. The identity, remember when we talk of identity element in a ring, we're always talking of the multiplicative identity, not the additive. The additive identity always exists, it is 0. So the multiplicative identity is the one we need. But you can check that if you multiply any element by 6, it doesn't change here. So 6 times 4 will give you 4 modulo 10, right? 6 times 8 will give you 8. So 6 times 8 is still, it's 48. So 48 gives you 8 modulo 10. Similarly, 6 times 2 is 12, which gives you 2 modulo 10. So 6 behaves like an identity because you multiply any number in here by 6 modulo 10, you get the same number. And 6 times 6 is 6, yeah? It's just the identity. So the multiplicative identity in this set is 6. Yet from the mother ring, the multiplicative identity is 1. So you can have a subring which has a multiplicative identity that is different from the mother. So anytime you have a subset and you want to check that's a subring, you have 2 ways to prove it. One way is to go through all the 9 properties that we listed earlier, but there's a shortcut which this theorem gives us. So if you have an empty subset of a ring, it will be a subring if and only if A minus B will be in the set S and the product AB is S. So it's closed with respect to this subtraction, if you want to call it that, or A minus B will be in S and AB will be in S. So if these two properties are satisfied, it is sufficient to conclude that S will be a subring of R. So that defines a subring. We may use this later, this theorem, to check if a subset is a subring. I think when working with ideals, I don't know if we'll do all that today. Maybe we'll still need to do one more class tomorrow. Complete this. So if R is a ring, if you can find some positive integer n such that NA is equal to 0. Remember, NA simply means adding A to itself n times. So if you can add A to itself n times to get 0 for any element in the ring, if this is true, then the smallest such integer will be called a characteristic of R. So this n must work for all the elements in the ring. So any element I pick in the ring, if I add to itself A times and I get 0, then it means the smallest such element will be called a characteristic of R. So please pay attention to this. This is not the English word characteristic or property. It's just treat it as a different word from the usual English meaning. So some of you normally write characteristics. No, it's not correct. It's just called the characteristic of the ring. So it may happen that this is not possible for some rings. So if no such integer exists, then we simply say that the ring is of characteristic 0. I think there's some people trying to join. Let's admit them, then we can continue. They have disappeared. So that's just a definition. This is something you will have to read again and again, but we'll look at some examples. So let's consider the ring of integers Z. Z is a ring. Now, if you pick any of the non-zero elements, no matter how many times you add an integer to itself, you will never get 0, right? So we say the ring of integers is of characteristic 0, because you'll never find an integer such that all the elements of a ring added to itself, added to themselves that number of times will give you 0. So the ring of integers is of characteristic 0. Now, number 2, if you consider the integers modulo n, this will be of characteristic n. So for instance, let's consider Z4. If you add any 0, of course, you can add it twice and you will get 0. And also if you add it 4 times, you will get 0. But the smallest number of times you can add 1 to itself to get 0 is 4. So if you add 1 to itself 4 times, you will get 0, modulo 4. 2, you can get 0 earlier than 4 times, because if you add 2 to itself twice, you will get 0. But you want a number that works for all elements in the group. So you just add, if you also add it to itself 4 times, you still get 0. 3, you can't add it to itself less than 4 times to get 0. So the smallest number of times you have to add 3 to itself to get 0 is 4. So it means if you add any element in Z4 to itself 4 times, you will get 0. And 4 is the smallest that works for all elements. You can have a larger number. So if you add 1 to itself 8 times again, for instance, you will get 0. but we are looking for the smallest number of times you need to add 1 to itself to get 0, and every other element in the ring. So 4 works for Z4, and we say that Z4 is of characteristic 4. Okay, so so here's a theorem, a fairly important theorem, which says let F be a field. Then the characteristic of F is either 0 or a prime number. So let's prove this. Suppose the characteristic of F is n. So we'll prove it by contradiction. Here it says that the characteristic of F is either 0 or a prime number. So we just need to show that if we assume that it is not a prime number, it will lead us to a contradiction. And therefore, it must be a prime number. So we start with that assumption. For the sake of contradiction, we assume that n is composite. Composite, it means not prime. So if it's composite, it's possible to write n as a product of 2 integers, where both of them are greater than 1. Both r and s must be greater than 1 if n is a composite number. It's always possible to find these 2 integers. So suppose n is equal to rs under these conditions. So if you add 1 to itself r times, and multiply it by 1 added to itself s times, you will get 1 added to itself rs times, right? You simply expand these brackets. So here r1 simply means 1 added to itself r times. So you can think of this one as 1 plus 1 plus 1 plus 1 r times. The same thing as this in brackets is 1 added to itself s times. So if you multiply it out, you will get rs1. Now we know that rs is n, and we know that the characteristics is n, so n1 must be equal to 0. Now it happens that this is a field, and therefore it must be an integral domain. A field is a division ring, a commutative division ring, and we show that every division ring must be an integral domain. Right? Now, being an integral domain, you're multiplying 2 elements in the integral domain. So this is 1 added to itself r times and 1 added to itself s times. And you're getting 0. The only way that can happen is if one of these is 0, because we are working in an integral domain. So because of that, it means we are able to find a smaller number r that works, right? For 1. This contradicts the fact that n is supposed to be the smallest number that works. So that can, when you add 1 to itself n times, you should get 0. So that means, that contradiction means that n cannot be composite and therefore must be a prime number. So you notice that we had to check with 1. 1 will solve your problems. Now, as an exercise, can you figure out why do we not need to check for the others? If you have checked for 1, the identity element, why don't we need to check for the other elements in the field? That's your exercise. Find out why. So definition, an element in a ring R is said to be nilpotent. This spelling is wrong. The correct one is up here, nilpotent. So R is said to be a nilpotent element if there exists a positive integer n such that a raised to n will be equal to to 0. So here is an example of an important element. If you consider the ring of 2 by 2 matrices over the real numbers and pick this matrix A, then you will see that if you square A, you will get 0. So A is this is an important matrix, because when you raise A to 2, you'll get 0. The other matrices which have to be raised to a higher number to get 0, this one was just a simple case where you only raise it to 2 to get 0. So such elements are called nilpotent elements. So here is another definition. An element is idempotent if you square it, it gives you the same element. So E squared is just equal to E. So in a ring with unity, 0 and 1 will automatically be idempotent elements. That is if the ring has unity. Remember, not all rings will have the multiplicative identity, but if it's there, then 1 will also be an idempotent element. 0 is always there because the additive identity and must be there. So let's look at Z8 consisting of all these elements. 2 cubed means you multiply 2 by itself 3 times, but we are working modulo 8, so multiplication is modulo 8. So 2 cubed is 8, and in Z8, 8 is 0, right? The same thing as 4 squared is 8. No, 4 squared is 16, which is 0 in Z8, right? So 2 and 4 are nilpotent elements in Z8. So we also have the following. 7 squared is equal to 1, because 7 squared is 49, which is 1 in Z8, right? 3 squared is 9, but 9 is just 1 in Z8. 5 squared is 1, because 25 is the same as 1 modulo 8. So 3, 5, and 7 are idempotent elements. We have seen some examples of nilpotent and also some idempotent elements. Yes.
In the definition, is it supposed to be an element A or just E?
I don't understand your question. In this definition, or?
Yeah, in the definition, because E squared give us, it means that, for example, 7 squared should give us 7. So I don't understand.
I made a mistake. Yes, you're right. You are right. So actually, we need to correct this. I don't know why I did not notice that at all. Thank you for the correction. Why did I write this? Okay. So I think Z8 may not have any idempotent elements, right? You have checked 7, 3, and 5. What was left? 6. Except 0 and 1. The only idempotent elements will be 0 and 1, right? Why did I put 7? Yeah, these are not idempotent. I think what I should have written here is that 3, 5, and 7 are not idempotent elements. I think 6 is also not. Yeah? If you have 6 squared is 36, that will not be equal to 6. Yeah, so then other than 0 and 1, there are no other idempotent elements here. The nilpotent elements, we have 2 and 4. So the correct statement here is that 3, 5, and 7 are not idempotent elements, and neither is 6 as well. We are not checked for 6. So we can't find any idempotent elements in this. So maybe as an exercise, you can try to find the idempotent elements of Z20 and also the nilpotent elements of Z20. I think there's such a question in your tutorial, so you will still find it there. If not in the tutorial, you check there's some typed notes which I shared earlier, and at the end of each topic in the typed notes, there's a set of questions. I think you will find a question asking you to find all the nilpotent and idempotent elements of Z20. So thank you for the correction. So the correct statement is that 3, 5, and 7 are not idempotent elements. So I think we can just go ahead and finish so that we don't have to meet tomorrow. Is that okay? So if you have an empty subset of a ring, it will be called an ideal if the following two properties hold. The first one is A minus B will be in S for any pair of elements I pick from S. And then the second property, if I multiply any element of S by some element from R, I will still get another element in S. So AR will be in S, and it doesn't matter on which end I multiply, either the left or the right, I still get an element in S, right? So this is a subset of R, but the claim is that if I pick any element in R and multiply by some element in S, I still get an element in S. So either on the right or on the left. So the reason we say either right or left is because not all rings will be commutative. If a ring is commutative, then this will be obvious. If it's a left ideal, it will also be a right ideal. But anyway, I think the definition is clear. If I pick any element R from S, from the ring R, and multiply by an element in S, I still get an element in S. And it doesn't matter whether I multiply the R on the right or on the left of A. I will still get an element in S. So you can also define left or right ideal. Right ideal simply means it works only when you multiply on the right. You can see the R here is on the right. Now left is in the brackets, so left simply means it only works if you multiply by R on the left, where R is some element from R. So there are some ideals which only satisfy this property, and those ones will be the right ideals. And there are some that satisfy only this property, and those will be the left ideals. But if both are satisfied, we just call it an ideal. So this one should be or. Actually, this and should not be here. I think I just copied what was up here and did not remove the and. So you just remove the and then the bracket will simply respond. So if you basically there are two statements. If you remove the right bit and leave only the left, then you'll have to exclude this bit, and you're left with only this right multiplication. I mean, this left multiplication. So and should not be there because it's misleading. It's basically, this only works if it's a left ideal. Any questions on this? So consider this ring of 2 by 2 matrices. You can check that this set is a left ideal. So what this means is if you pick any other 2 by 2 matrix and multiply it on the left of a matrix from S, you will get another matrix in S. So you can also show that this other set is a right ideal. So how do you show that? If you pick any other matrix from any other 2 by 2 matrix and multiply it on the right of a matrix from T, then you should get another matrix in T. So these are two examples of a left ideal and there's a right ideal. I have left this up to you. Just pick any 2 by 2 matrix, multiply it by a matrix in S and check what you get, whether you will end up with a matrix in this form where the first column is 0 and you don't care what is in the second column as long as they are real numbers. Check with the second set T as well that it is a right ideal. So multiply, pick any matrix, 2 by 2 matrix, multiply it on the right side of a matrix from T and confirm that you will get another matrix of this form where the second row is 0 and the first row we don't care as long as they're real numbers. So here is a homomorphism for rings, the definition. So if we have a map from R to S, where R and S are both rings, which satisfies these two properties, then we say F is a homomorphism of R into S. Now, it is possible for the two rings to be totally different. It's possible for the addition in R to be different from the addition in S, and also the multiplication in R to be different from the multiplication in S. So what happens here is that this A plus B will be the addition in R, and on this end, F of A plus F of B would be the addition in S. The same is true for the multiplication. This AB here will be the multiplication in R, and F of A multiplied by F of B will be the multiplication in S. So if F is injective, we call it an embedding. If it's bijective, we call it an isomorphism, and in that case, we say this spelling is it's wrong. It's supposed to be isomorphic. It should be a P here. You can note that this should be isomorphic. So if you have an isomorphism between two rings, then we say that the two rings are isomorphic. We will not do much more on that. I think you will cover more of this in the next algebra course. So here is a theorem that gives you some properties of homomorphisms of rings. So if you have a homomorphism F from R to S, the following properties will hold. If 0 is the 0 of the ring R, then it will be mapped onto the 0 of the ring S. You can hear me?
Yes.
Good. So, and also if A is an element of R, the additive inverse of A will always be mapped onto the additive inverse of the image of A. So all this can be proved, and all the proofs are available in the handwritten notes I shared. the link. You have a link where you can download all the handwritten notes. I think it's lecture 15, if I'm not wrong, of the handwritten notes. You will find the proofs of all these points there. So, full proof. So the image of the homomorphism is also a subring of S. So this is where you'll use the theorem that helps you to check if a subset is a subring to prove this. And then the kernel is a set of all elements in R which are mapped onto the 0 in S. And this is called the kernel of F. It turns out that this kernel is actually an ideal of R. So again, you will get the proof for all these in the handwritten notes I shared, the full proof. If R is a ring with unity, then the image of 1 turns out to be the multiplicative identity of the image of F. So the image of F is a subring of S, and it will have the identity of the image of F as a subring will be the image of 1 under this map F. So remember earlier on, we saw that a subring can have an identity which is different from the mother ring. That's why here we're very specific that F of 1 will be the unity of the subring image of F, where the image of F was defined here, number 3. So the last property says if R is a commutative ring, then the image of R or the image of the map F will also be commutative. The image, of course, we have seen this FR is also the same thing, the same set as image of F. So image of F means the same thing as F of R. So if R is commutative, then the subring onto which it is mapped in S will also be commutative. So I think that's all for all we had to do. We will not have another class now. I think this is the last one we'll have. You will learn more about rings in the next algebra unit with the SMA 405. There'll be a lot more stuff about rings. This was just to introduce rings, and you may have done a bit of rings again in SMA 205. So are there any questions? So make sure you check the proofs. I have shared the properties here, but I didn't put the proofs in the slides. So you need to go and check the proofs. They're in the handwritten notes. So we will stop there for today.